Hello again. All right, so we're going to look at events themselves. And so we're going to try to define our events. And so we can have a simple event, which is an event. Remember, our definition of event was one or more outcomes from a sample space. So a simple event is a single outcome. And for example, let's say I am rolling that d6. The event of rolling a 4 is a simple event. I have a deck of cards, and I draw from a shuffled deck a King of Hearts. That's a simple event, because it's only one of all the options in a sample space. So a simple event is a single outcome, an event that consists of a single outcome. Our book has a other answer, the other side of this, which is things that aren't a simple event. And the word we have for that is not a simple event. And so any event consisting of more than one outcome is not a simple event. Well, let's look at a slightly more complex sample space. I will roll an 8-sided die, and then I will toss a coin. So I could, for my 8-sided die, I'll do my coin first. I can get a head, or I can get a tail. And then I go to roll my die, and I can get a 1, 2, 3, 4, 5, 6, 7, 8. And then if I flipped a tail, I could get a 1, 2, 3, 4, 5, 6, 7, 8. Join all these together. And so my sample space, for again, lack of a better notation, I'll go heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, heads 7, heads 8. Am I staying on the screen? I stayed on the screen. I like when that happens. Tails 1, tails 2, tails 3, tails 4, tails 5, tails 6, tails 7, and tails 8. And notice, if I count these up, there are 16 outcomes. And so a simple event would be flipping heads and rolling a 3. And we'd write that as H3, and that's a simple event. A not simple event would be flipping tails and rolling odd. That event would be T1, T3, T5, T7. And so there'd be 4 outcomes in that not simple event. And so we have some nomenclature. We're beginning to talk about how we can work our way through. And one of the things that we can do with this is we can notice that when I had tails, heads or tails, and then in a D8, this gave me 2 possible outcomes. This gave me 8, but together My sample space had 16 possible outcomes. And notice I did 2 times 8. And so this is called the fundamental counting principle. I'll just abbreviate principle like that. And what this says, if one event can occur m ways and another event can occur n ways, if they happen in sequence, one after the other, there are m times n ways. And so we can count up all of our possibilities by this multiplication rule that we can have coming out. And so this fundamental counting principle says, hey, if I need to deal with the different ways things happen, I can count them up, and then if they happen in sequence, then I can multiply them together. And so let's look at an example of this at a wedding, right? And we'll go to a crazy wedding here, where you get your menu options, right, on your invitation, and they'll say, what meat do you want? And your option is some beef, some chicken, fish, or a vegetarian. Right, your protein's going to come. I guess protein's the better way to say it now, since the vegetarian options are good with protein. And so you have beef, chicken, fish, or veg. And then you had some type of starch, like potato, stuffing, and rice. And then maybe a vegetable. Let's see. Peas, carrots, corn, or broccoli. My favorite. Gee, I can't even spell it, I know. And then dessert. And we could have cake, pie, or pudding. And so those are your menu options. Well, I could think about having every possible dish. There are many different meals here. In fact, I have 4 meat options, 3 starch options, 4 veg options, and 3 dessert options. And so if I put these all together, there are 144 different dishes I could have, different meals I could have on a fairly simple menu combination. In fact, it's one of the things I try to think about every now and again is like, how many different build your own slams could I get at Denny's? And you actually, as we work our way through this unit, we'll be able to answer that question. Right? You have toast, 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 and toast. Right? But toast, sausage, sausage, and toast is the same as sausage, sausage, toast, and toast. But we'll look at the meal, Sam. But our fundamental counting principle says all the combinations. And what do I mean by combination? Like in a beef, potato, peas, and cake. Or I could have beef, potato, peas, and pie, and so on and so on. It's actually a psychologically known phenomenon. It's called choice fatigue. That because when you have a lot of options, all the combinational possibilities we try to manage. And they're starting to see this, especially in Western cultures, where you can walk down a salad dressing aisle and have 50 types of salad dressing. And so in your brain, you're going, okay, I want Thousand Islands, and I'm going to have that with a salad. But the salad I want is going to probably be a spinach with a walnut. And your brain has to organize the choice of all the different meals you can make. And they're finding that the more individual choices we have, the actual harder it is for us to make decisions. In a way, you'll say you're spoiled for choices. but your brain tries to manage all the combinations. And you can see quickly how large these numbers go. In fact, one of the things that we're going to see is numbers grow rather quickly. The more choice you have, the possible outcomes get larger. Our probability spaces grow with the different choices or the different things within the sample space and putting events together. So let's look at another way of thinking about this. Let's think about a 6-digit 1, 2, 3, 4, 5, 6-digit passcode. And we're going to say that you can only use the numbers 0 through 9. Well, in the digits 0 through 9, there's 10 things. And so the number of combinations I can have is 10 times 10 times 10 times 10 times 10 times 10, or 10 to the 6th, which is a 1 with 6 zeros behind it, right? There are a million combinations of a 6-digit number, which makes sense. If you think about it, you put all zeros in there, or you put all nines in. So all nines is 999,999, and then you add the 1 for all the zeros, you get your 1 million. But let's do something odd. Let's say, hey, you can't repeat a digit. And so when I choose my first digit, I'll bring that down here, I have 10 options for the first digit. So I'll come down, I have 10 options, and I choose a 2. And so now in my second digit, I can't choose a 2. I only have 9 options. I reduced it by 1. And then in my third option, well, I can't do any of the first 2 numbers, so I reduced it by 1 more. And then I can't do any of these first 3 numbers, so I've reduced my options by 1 more. And then I can't do any of these first 4 numbers. And so see how I'm reducing the options I have when I can't repeat a digit. And so I run over to my calculator here. Run. See, this is me running by clicking this button. And then in clicking this, and I turned it off here. And so I had 10 times 9 times 8 times 7 times 6 times 5. Now we're going to find another way to do this, but for right now, what we want to do is look at the number that comes out of this and see what we get from it. So 10 times 9 times 7 times 5. Let me come back over here. Sorry, switching screens sometimes can be a bit weird. And so if I have 6 digits, but I can't repeat any, I have 151,200 possibilities. About a factor of 10 less because of the lack of repetition. This is one of the things we're going to want to start building, is finding ways to count very large things fairly quickly. All right, I'm going to put this segment up, and then we're going to look at probabilities. So we've talked about the sample space. We've talked about counting up large quantities of things, which will help build sample spaces. Now and outcomes and events, and then we're going to look at probabilities themselves.